So, what are collective communications? Gather, scatter, broadcast, all to all. Okay. So, where everybody is involved. So, broadcast was the first one. So, you can broadcast to everyone. Okay. So, this buffer will be sent to everybody. So, this is the same picture we write it for Python. So, A0 is what I am sending. So, this is a processor. So, the 4 processor, processor 0, processor 1, processor 2, processor 3, and this data, the 4 data. Okay. So, in fact, this is a nice presentation, I took it from somewhere. So, this A0 is a one data is with processor 0 and is going to be sent to everybody, right. So, this, all the processors have this A0, one data. So, broadcast. The way to do is broadcast, send buffer. So, buffer was a array. So, I just send the 0 thing and size 1 MPI int da da da. So, everybody has it now, this buffer, they are printing it from rank 0, from rank 2, rank 1. So, broadcast message. Okay. So, this broadcast, radio broadcast going to everywhere. Scatter. So, scatter is, I have processor 0 has 4 data. By the way, number of data and number of processors must be the same for scatter and gather. Okay. So, 4 data processor 0, but is sending 1 data each to different processors. So, 0 will retain 0, but processor 1 will get A1, this one, processor 2 will get A2 and processor 3 will get A3. Okay. So, this scatter and gather is reverse process. So, processor 0 has this, all the processors, every processor has 1 data each and it will be assembled in processor 0, or it could be any processor, by the way, you can gather anywhere. Okay. So, gather is just reverse. So, syntax is different. Huh? So, the name of the function is this, and so I am not going to dig deeper into this. Well, rather I will not describe this. All gather. So, all gather is every processor has 1 data each. Okay. Now, they all be gathered. So, processor 0 will get all 4 of them like this. Processor 1 will also get the same thing. So, everybody is gathering the data all to all. So, we have big array which can be partitioned and sent to everybody, but so whether every processor has different data sets. So, processor 0 has this data P0, processor 1 has this data, 2 has this data, processor 3 has this data. So, this processor 0. Okay. So, what is being done? A0 will keep the A0 with itself, sorry, processor 0 will keep A0, but send A1, A2, A3 to other 3 processors. So, A1 has come here, A2 has come here and A3 has come here. What does processor 2 do? It keeps V1, the diagonal entries are kept with itself. So, B1 is here, but other ones like B0, B2 and B3 are transferred. So, B0 goes to 0, B2 goes to 2 and B3 goes to 3, processor 3. So, in fact, it is a transpose, these are so called transpose. So, you can see the diagonal is remaining the same, but A1, A2, A3 has come down, right. The row has become column and column has become row, but this for single data. Okay. What if I have lot of data in A1? So, this could be a big array with 4 processors only, then what will happen? It divides equally. So, this could be 1024 data points, then each guy will get 256. So, it is one, it is just going to take one big line and cut and distribute the piece. This is very useful thing for FFT, which I did not do in this course. So, fast Fourier transform will require this all to all. Okay. So, any question? Well, I mean this we have done it before. I see quite a few are bored, but let us finish it for completeness.
Sir,
Yeah.
in gather operation, we
Uh.
have to also take care about if the data is large, then we cannot send all the data in one processor.
Yeah. So, data. So, one option is which I have not checked this. So, gather is this could be maybe 4 data points, 4, 4, 4. So, 16, right, total 16. So, 16 will accommodate here, this will be 4, 4, 4.
But if the data is large, then we have to.
By the way, well, practically speaking, we do not do this gather well, yeah, why can't it be, sorry, why can't it be done? Gather can do it.
I mean, sir, if the in individual processor, if the data is large,
Uh-huh.
and if we are sending those arrays or those lists to one processor,
Okay.
and the first processor we are sending all the data to the first processor.
Okay.
The first person already has a data which is very large.
No, no, no. They are different allocation. You have to create the location for space for them. This space is already there here in this space. You have to have the space first. Without that, it can't come. In fact, function won't work if there is no space. So that's why the size is specified. Okay. So size is nobody says the send count. This will make sure that the variable is there. Otherwise, it will just throw up the error. But gather is normally for I don't know what you are doing for this right now. This for final difference.
Yeah, like for printing the data, I was trying to accommodate all the data in one processor. Maybe it's better to print separately.
Print separately. Each guy separates. Just put that thing. Actually, it's not. If it's a big data, so let me just say this. So I am using, let us say, 1000 processors or 10,000 processors, and I have array velocity field u. So, will I gather this data from 1000 processors? The data could be 1000 cube. Okay. No way, you should not gather it in master, because master will just get full. Okay. So, data should remain there, but what normally we do is we create energy, local sum. Local sum is a number which should be gathered. Okay. In fact, I will do reduce for local sum. I am going to come to that. So, something which you need only one number each, then you gather. Big data, you do not collect it. And printing, debugging, of course, we need to print. So, give the ID and print. So, reduction operation. So, MPA reduce, we done it for sum. This is a good example for sum, just one line. Do not do I gather. So, we are doing summing some local sum. So, just do reduction. So, MPA reduce. So, what are you reducing? Okay. So, local sum, this is local sum. Where? So, this will be sum, and what operation? So, operation is here op. Rest all are trivial. Okay. So, I am not counting is number of data points. And where should it go? Answer. Answer we want it to come to the root master. So, you can also do all reduce, which I am going to show you by example. So, this is the data. So, processor 0 has 10, P1 has 20, P2 is 30, P3 is 40. It could be local sum. So, when I say reduce, then reduce sum with plus. So, they add up and comes to the root. It comes to one processor. It could be somebody else, but I recommend root. Or reduce, it goes to everybody. Scan is another useful function. So, scan for plus. So, this operation is again plus. So, first guy will do the first sum, which will be trivial, no summing. These two are added together and comes to second. You got it? A0 plus A1 is going to the this is an array, this is receive buffer. So, I want to do partial sums. So, it is like scanning, no, scanning, well 10 put it here, 10 20 put it 30, 10 20 30 3 together it comes here. Next scan further 40. So, this sum all 4 of them I put it here. So, these are useful for some computer science algorithms, but I have not used it ever. Reduce scatter is another interesting function, which again I have not used it at all. So, sum the first, this for plus, okay, all of it is for plus. So, the first entry of each of these processes 1 1 1 1, add them and put it here. So, this is a receive buffer. Second row, add them, put it here. Third row, put it here. Fourth row, put it here. Okay. So, these are functions given to the user. You do not need to write, if you are doing something like this, then you do not write yourself, you use the function. If they are optimized function, they use various smart algorithms inside. The reduce, do not do it yourself. Reduce does like tree kind of stuff for sums. You understand what I am saying? So, if I have lot of processors, how will I sum? So, I do not go in line sequence. So, it is not going to go like this. What it does, it create partition in half, then create well, I would like to do sum for this, sum for this, but then this can be again partitioned in half. So, you do create a tree kind of structure and do the sum. So, MPI reduce which we use often. So, the result is coming in process 0 and it is a receive buffer, we will get the answer and I am printing them. Okay. By the way, the result is coming to only one of them, but if you print, then all of them will print of course, because this receive buffer exists everywhere. Okay. So, in fact, there are zeros except processor 0, which is 100. So, what should we do when I have reduce? For printing, you say if rank 0, then print. So, MPI you should be careful, who has the data, that guy should only print. Okay, now, these are some numbers for MPI with O3 operation. So, this is a processor actually, not thread proc. So, it turns out there is a for 8000 by 8000 there is a significant speed up. Same thing which I wanted to see whether there is a problem with compare with multi-threading. This number is reduced, but not so much. Well, actually multi-threading this was doing okay, OpenMP, but Python was doing badly. It turns out this one does not have any false sharing issues. Why it does not have false sharing issues? Because memory is not shared. Okay. So, this was y equal to ax. So, y was a big array, right, and problem happens if y is a big array, like here y is a no sorry y is not a big array, y is array, but which is affected by operations here for x 8000, no y is a small array. So, this is a false sharing issue and it acts at the edge while updating. And this kind of, so since data is separate in separate processors, false sharing does not occur for MPI. Okay. So, MPI is in fact is clean in terms of memory management, no false sharing, roughly similar, but MPI appears to be faster, which is counterintuitive, but this because of all this false sharing and this kind of issues. And C++ code is with O3 option is faster than Python.